I will talk about an approach to regular separability problem in languages of vector addition systems. And this is a joint work with Georg Zetzsche. So first I will define regular separability notion, and I will recall what are vector addition systems and their languages. Then I will tell you about our motivation and a brief history of the problem, and I will state you our main result. And then the rest of the talk I will devote to telling you about our techniques. So I will try to show you the intuition behind our proof, because I think that maybe our techniques are even a bigger contribution than the theorem itself. Okay, so what is a separability notion? Imagine we have two sets or languages, K and L. Let's say they are disjoint, and then we say that set S separates them if it's like on the picture, so K is included in S and S is disjoint from L. Okay, and we say that languages K and L are regular separable if there is some regular language S which separates them. Sometimes we say shortly reg separable. Okay, and now let's recall what are vector addition systems with states. So such a d-dimensional vector addition system with state, shortly d-VAS, it consists from a finite set of states Q and finite set of transitions. Every such a transition has a source state, target state, and effect is a d-dimensional integer vector. And if we are talking about labeled VASes, if we want to talk about languages, then such a VAS comes with a labeling of transitions by letters from some finite alphabet, let's say sigma. And how these transitions are applied: if we are in configuration with state P and vector U, which is a vector in with non-negative entries necessarily, then we can fire such a transition which has source state P, target state Q, and some effect V, and then we go to a configuration with state Q and with vector U plus V, under the condition that U plus V is non-negative on all the coordinates. Okay, so I hope it was just a reminder. And so that's why I define it so briefly. If we want to define a language of a VAS, then we need to specify source configuration and target configuration. And then language of a VAS with such fixed configurations is defined naturally. So it's just a set of words which can be read on paths leading from source configuration to target configuration. What is important here is that we have an acceptance condition, but by a single configuration, not by a state. Yes? Okay, so what is a regular separability problem for VAS languages? You are given two labeled VASes with transitions labeled by letters from finite alphabet. These VASes are A and B, and we ask whether their languages are regular separable. So what is a motivation for us to study this problem? I can say that this motivation is twofold. One comes from VASes and another comes from separation. So first of all, VASes are a very fundamental model which is still not well understood, and it needs deeper understanding. So for example, this very fundamental problem of reachability is still complexity is not really understood, but also many other problems lack understanding, and this is one motivation. And one way to gain understanding is to study VASes from a bit different perspective, because maybe it gives us some new insights which we haven't thought before. And one such possibility is to study separability problem, which which is a very natural problem, which was maybe not so so much studied, but recently it's studied more, and we can observe that, for example, separation generalizes reachability problem for VASes, because if we say about languages of VASes specified by source and target configuration, then the reachability problem is just question whether language is empty. So maybe we can generalize it and talk about more sophisticated problems which somehow use more structure, and maybe this will give us some interesting insights. So this is, let's say, our motivation to study this problem. Short history. We conjecture that this problem is decidable in general, but it's open. We don't know it. But the problem is solved in a few subclasses. It's known to be decidable. For example, it's known that if our input are one-dimensional VASes, then the problem, so in other words, one counter nets, then the problem is decidable and also p-space complete. Similarly, if our input are so-called integer VASes, or we can say shortly Z-VASes. So what is a Z-VAS? In a Z-VAS, we don't demand that our path should be necessarily all the time above 0 in this positive quadrant. In a Z-VAS, the path can go below 0 in any dimension as much as it wants. So this is a Z-VAS, and the problem is also decidable for Z-VASes. Similarly, for commutative closure of VASes, which happen to be also a subclass of VAS languages, and also for languages of VASes but with different acceptance conditions, so with acceptance not by target configuration but by set of target accepting states. So all these subclasses are solved, and our main result kind of generalizes this. So our main result says the following, that the regular separability problem is decidable if we ask about regular separability of general VAS language on one side, and on the other side, language of a VAS coming from some subclass, either one-dimensional VASes, or VASes accepting by state, or integer VASes. So you can see that this generalizes 3 of the 4 points from the previous slide, and the 4th point is also generalized because it can be reduced to the VAS versus Z-VAS case. And what is maybe more important is the technique. We achieved this by a uniform technique, and we hope that maybe this technique can be used in the future to solve a general VAS regular separability problem. And in the rest of the talk, I will present you this technique. Okay, so what is our first observation? So let us fix an alphabet AN, which consists of 2 n letters, U1, D1, U2, D2, and so on. And U1 corresponds to a going up in dimension 1. D1 letter corresponds to going down in dimension 1. U2 corresponds to going up in dimension 2, and so on. So if you have, for example, a word U1, D2, it corresponds to first going up in dimension 1 and then going down in dimension 2. So you can observe that words over the alphabet AN, they correspond to such a walks in n-dimensional grid. And we will use this connection, and in that way we can define a language Zn, like 0 n-dimensional, and this will be a set of words which correspond to paths which, let's say, start in 0, they do some walk and they finish back in the same place, in the 0 vector. So their total effect is the 0 vector. and we write z paths because we don't demand that they stay in the positive quadrant. They can travel also below 0 in every coordinate. Okay, so what is our lemma then? So our lemma says that for any vas A and z vas B, one can compute a vas C over the alphabet AN such that languages of A and B are regular separable even only if language of C and our language Zn are regular separable. Observe that Zn is clearly a language of the Z-vas. So what it gives us is that we can actually reduce our vas versus Z-vas separability problem to a similar vas versus Z-vas separability problem, but when a Z-vas is fixed. And observe that now separators are such regular languages which contain language L of C but are disjoint from language Zn. So our next step will be looking what are the potential candidates on these separators Zn. What regular languages are disjoint from our language Zn? Okay, let's come back for a moment to the other cases. As I said, I will focus mainly on this case of vas versus Z-vas, but let's briefly say how it works similarly for the other cases. So when we have this alphabet AN, Zn is our language. Dn is the similar language, set of words corresponding to n paths of effect equals 0. So paths which start in 0 vector, but they all the time stay in the positive quadrant, and they also come back to 0 at the end. And Cn, it will be a set of words corresponding to n paths which start in 0, but they don't have to finish in 0. They just have to stay in the positive quadrant all the time. And then our result says, a theorem in our paper, that in the case of vas versus Z-vas, we can reduce to the case when the Z-vas language is fixed, and it's exactly Zn. In the case of vas versus 1-vas, we can fix the 1-vas language to be D1, and in the case of regular separability of vas versus vas accepting by state, we can fix the vas accepting by state language to be exactly Cn. Okay, but let's come back to our vas versus Z-vas case. So our key lemma is like that. So recall what was AN and what was Zn. And as I said before, our problem actually boils down to understanding what kind of which regular languages are disjoint with Zn. And this lemma characterizes such languages. So lemma says that if R is over alphabet AN is a regular language, then R has empty intersection with Zn if and only if R is included in a finite union of basic languages. And we have two kinds of basic languages, modulo language and drift language. And of course, I have to tell you what are these languages on the next page. So what are basic languages? First, simpler kind of basic language is modulo language. So n is a number, and language Mn is a set of words corresponding to Z paths with effect which is not equal 0 vector modulo n. So it's quite simple to see that Mn and Zn are actually disjoint, because Zn contains these paths which have effect exactly 0, and Mn does not contain such paths and also some other ones. And it's also easy to see that Mn is a regular language, because its automaton just have to remember the current effect modulo n on every coordinate. And we have a second type of our basic languages, which is called a drift language. it's a bit more sophisticated. So it's duk. U is a vector, n-dimensional one or d-dimensional one, and k is a positive integer. I will draw it to present it easier. So here we have a vector u, here we have some perpendicular line to it. And duk contains words which correspond to z paths which somehow deviate into direction u, for example, like that. So this blue path, it rather goes into direction u, but sometimes it comes back. So a path, in order to be in duk, it has to never come back more than k. So like on our picture. Here this path comes back a bit, but not more than k. And additional condition is that this path has to be at the end not equal to 0. So it's easy to see that duk is definitely disjoint from that end because it doesn't finish at 0. And maybe it's not immediate to see that this is a regular language, but it's also not hard. But I will not prove it now because we don't have much time for it. Okay, so these are our basic languages. Let us recall our main lemma. It says that actually we have characterized which regular languages don't touch language ZN. And I think this result can be of independent interests. Maybe, I hope maybe it can be used in some research, not really concerning separability problem. Okay, let's go further. I will try to show you intuition behind the lemma, the proof of this lemma. Okay, so let's recall the lemma. And first, we can assume without loss of generality that if we look at the automaton of our regular language, then directed acyclic graph DAG of strongly connected components of this automaton is a line. So I mean strongly connected component, then a transition, then a component, then a transition, and so on. So every automaton can be decomposed in a finite union of such simple automata. So therefore we can assume our automaton is of such a form. And if we have such an automaton, we can define a key notion, cone of an automaton. And let's look at simple cycles on our automaton. So paths from some state q to the same state q. And such a cycle is labeled by some word, and because this word is over alphabet an, it corresponds to some vector. So now let's look at these vectors, effects of all the simple cycles in our automaton, and let's look at the linear combination of these vectors with non-negative real numbers. So non-negative linear combinations of these effects, and this is what we call a cone of automaton A. So it can be shown, not very hardly, that such a cone always either equals the whole space, d-dimensional or n-dimensional in the case of so maybe that's a typo. It should be Rn because our alphabet is n-dimensional. So such a cone always equals n-dimensional space or is included in some half space. I will not go into details, but we can show that if cone of some automaton actually equals the whole space, then our language is included in some modulo language. And in the other case, if a cone is included in a half space, then we can divide our language into a part which is included in I think one drift language and another part which stays close to the border of this half space, and in that case we can use induction assumption for smaller dimensions. So actually here we use an induction over number of dimensions. Okay, so this is roughly speaking how we have shown this lemma. So recall one more time this lemma, and now our question is, we are given a vase and we actually have to tell whether this vase can be separated by a regular language from language Zn. But because of our lemma, this is equivalent to a question whether language of this vase is included in a finite union of modulo and drift languages, because only finite unions of modulo and drift languages are regular languages which don't touch Zn language. Okay, so how do we answer this question? This is actually quite sophisticated, but I will give you a few ideas. How do we test this inclusion? So first of all, it's actually quite similar to the proof of the lemma, which I just have mentioned. We also look at the cone of A, but now A is not an automaton, but A is a vase. So operating, pasting and cutting cycles in a vase is not so simple as in the automaton. We have to be much more careful. So we use the known tools. We use the KLM decomposition, Kossaraju-Lambert-Meyer decomposition, the kind of decomposition which was used to decide reachability problem for vases. And based on this KLM decomposition, we are able to design a regular language which over approximates our vase language, but somehow behaves similarly. And based on that, we are able to test this inclusion. But I don't have time to go into details. Okay, that's all I wanted to say. Thank you very much.